Hi, I'm Lazpita, a PhD student, part of the Model Flows group, and today I want to present you my work about unraveling the generation and destruction mechanisms of our vortices in urban flows. This work has been presented last summer on the second Spanish Fluid Mechanics Conference and also has been published into different journals with the name of On the Generation and Destruction Mechanisms of our vortices in urban fluid flows, and also data-driven assessment of our vortices in simplified urban flows. So if you have any doubts about the talk today that is going to summarize these works, you can check out these two references. So the guideline of this presentation will be the one that you see. Will I introduce you to the problem, then speak about the urban flows and the main flow features they have. Afterwards, we're going to make a pattern analysis of these flows and finally give some concluding remarks. So, as we all know, one of the most endangering things right now in the world is the air pollution, and especially in the cities where we have many different sources such as industrial, transport, commercial, even residential source, and this creates two main great issues in this problem, where one would be the accumulation of these pollutants in the urban areas, and the other one, and also like a consequence of this, is the urban heat island, where basically we have a peak of temperature in the inside of the cities compared to the urban areas that may cause many different bad consequences. And finally, just to give a data point, the cities are the cause of more than 60% of the total greenhouse emissions. So this is a problem we have to try to palliate in the following years. So how can we help these problems? And first, we can try to simulate in this kind of urban areas, but these simulations are really difficult because it involves a very complex flow that has turbulence, different structures of the buildings, different conditions. It's really high. It has a really high computational cost. We have different conditions on the cities and stuff. So it's a really difficult thing to model and to simulate. So in our case, we are going to focus on a simplified environment where we have two mounted obstacles aligned with the incoming flow and with a separation L, as you can see in the screen. And this separation, we will change this separation to obtain three different cases, which are the skimming flow, the wake interference, and the isolated roughness. Sorry. So, our simulation, it has been done using large eddy simulation, LES, incompressible Navier-Stokes equations. The solver we have used is the NET 5000. Reynolds number is 10,000, and the inlet condition is the below turbulent boundary layer. For more information, you can go to the link to the paper you see here. Then, once we obtain these databases of a simplified environment of our urban flow, we compared our simulations with the ones they obtained in Monnier et al. In this reference experimentally, and we can see some similarities where we can see the stringwise RMS velocity on the side of the buildings, the spanwise RMS velocity in the second building, in the wall of the second building, and the vertical structure that appears after the first obstacle. Also, focusing on different studies, we can see that our different simulations have this kind of R vortices that will be the main topic of our talk, but also the horseshoe vortex that appear in the bottom of the buildings that may help us identify different flow features or characteristics of the flow. And well, once we have these databases and we know what flow features we may encounter on these urban flow areas, we will want to analyze these patterns, these features, and for that we are going to use different tools based on model decomposition. And the first one will be the proportional decomposition, where we decompose our snapshot matrix into 3 different matrices, where we have the left eigenvector matrix, the singular values, and the right eigenvector matrix. We can reduce the dimensionality of these matrices to help our code, but also to obtain the POD modes. If we take the left eigenvector matrix, this would be the POD modes that can identify different spatial patterns. And that's what we are going to do. We're going to apply this code to our database, and we obtain the different POD modes. Here we represent the first 5 energetic modes for the streamwise and spanwise velocities. And also we are going to focus from now on, as I want to be brief, we're going to focus on the skimming flow analysis. If you want for more information on the papers I mentioned, you can find out a more extensive description of this analysis. And if you focus on the first 2 most energetic modes, we can see that they are similar and that they are focused more on the fluctuations between both sides, and this may encourage us to say that they are related more in the breaking process of the main features, and thus these breaking mechanisms are the ones that are more energetic. And if you focus now on the lower energy modes, we can see that they are more focused on the wake and the generation of the structures. And this will also help us identify further patterns. So if we want to do a temporal analysis, we will have to go to different algorithms. And in our case, we're going to use the higher order dynamic mode decomposition. And that is well explained in this book, where you have different examples or even the code, so you can check it out. But basically what we are trying to do is, with some kind of windowing process, obtain the different DMD modes that have an associated amplitude, growth rate, and frequency. If we apply this to our urban flows database of, again, the skimming flow, we will obtain some kind of frequency spectrum where we have different temporal modes, and we can see like 2 different type of modes, where we have the low frequency modes and low amplitude modes, and the ones that are like higher frequency and higher amplitude modes. And if we check the structures that appear here, we can classify into A modes, that are the ones that appear in the lower frequency part of the spectrum, and are related more to the generation of these main flow structures, as you can see here. And we have like some kind of a dome that is helping the recirculation for the arc vortex, also, you can see like some kind of the horseshoe vortex influence here. And if we go to other type of modes, such as the B mode, which is more related to the breaking process of these main flow features, we see more like clusters in the side of the buildings, and that help the destruction and the dispersion of these structures. And this has been the most relevant results of our study. And as concluding remarks, to repeat again that we have different flow features for each regime, but this is like the summarized analysis of it. If you want to know more, you can go to the papers. The POD reveals many spatial patterns and the energy associated to the different type of modes. And with that, we can help identify the temporal modes where we saw that the generation modes, with lower frequency, and that help the recirculation to the interior of these vortices. And on the other hand, we have the B modes that have higher frequency and also a higher energy associated. and create this turbulent wake and help the pollutant dispersion of the cities. Well, as I said, I'm part of the model flows group, and here and we have a web where we put all of our code. So if you're interested in using the code that I've showed or the other type of algorithms that we have for pattern analysis or even prediction and reconstruction, you can check out our web. And that was all. Thanks for your attention. And if you have any question, you can put it on the comments or send us an email or even visit our web to see our other different works and codes. Thank you.